Mars is trending again. Private companies are building rockets. Governments are signing partnerships. The narrative is seductive. But here's what they don't show you. The first colonist struggling to breathe as dust clogs the air filters, the emergency alarm when radiation shielding cracks, the slow realization that the supply ship from Earth won't arrive for another 18 months. And here is a question. If you were the first human to set foot on Mars, what's the very first thing you'd do? Comment down below. I will pin the most creative answer. Now let's begin. I'm not here to kill your dreams about space exploration. I'm here to show you why our cosmic journey needs to be grounded in reality, why understanding genuine challenges makes our eventual success more meaningful, and why Mars teaches us just how extraordinarily rare and precious the conditions for life actually are in this universe. The data I'm sharing comes from actual missions. NASA's CHAPIA program, that's the Crew Health and Performance Exploration analog, has been running simulated year-long Mars missions right here on Earth since 2023. The European Space Agency published comprehensive reviews on life support system failures in 2024. Recent studies on bioregenerative systems, the kind we'd absolutely need for Mars survival, revealed failure rates that should terrify anyone planning interplanetary colonization. This isn't speculation. This is what happens when you take the laws of physics, the realities of biology, and the limits of current technology, then try to make them work 300 million kilometers from home. Let me paint you the real picture of what a Mars colony actually faces, step by step, system by system, using data from the missions that are there right now, and the simulations running as we speak. The first challenge isn't the one most people think about. It's not radiation, though we'll get to that nightmare. It's not even the toxic soil or the unbreathable atmosphere. The first thing that starts killing a Mars colony is something far more mundane but absolutely critical: mechanical failure rates in low pressure, high dust environments. The Mars rovers, Curiosity, Perseverance, the late Opportunity and Spirit, these machines were designed by the brightest engineers at NASA and JPL. They underwent years of testing. They represent hundreds of millions of dollars in research and development, and they're constantly breaking down. Opportunity's mission was supposed to last 90 Martian days. It survived for over 5,000 sols, which is remarkable, but it eventually died when a dust storm covered its solar panels and it couldn't generate power. Spirit got its wheels stuck in soft soil and couldn't free itself, then froze to death during winter. These were robots that didn't need air, water, or food. They just needed to move and collect data. And Mars killed them anyway. Now scale that up to a human habitat. You're not maintaining one rover, you're maintaining life support systems that recycle air, purify water, grow food, regulate temperature, manage waste, generate power, and handle 1,000 other critical functions. Every single one of those systems has mechanical components: pumps, valves, filters, sensors, motors, seals. And every single one of those components will fail faster on Mars than anywhere on Earth. Why? Because Martian dust isn't like Earth dust. Under electron microscopes, Martian regolith looks like microscopic shards of glass mixed with rusty razors. The particles are so fine, we're talking less than 30 micrometers in diameter, that they penetrate seals designed to be airtight. They're charged with static electricity from the planet's dust storms, so they cling to every surface and work their way into every gap. The dust doesn't just coat things, it abrades them, it grinds down moving parts, it creates false readings in sensors, it blocks filters faster than you can replace them. And here's the cruel reality: you can't just order replacement parts from Amazon. Every component has to come from Earth on a cargo ship that takes between 6 to 9 months to arrive, assuming perfect launch windows that only open every 26 months. A 2024 study on environmental control and life support systems, ECLSS for short, found that even in controlled Earth simulations, these systems require constant maintenance and experience regular component failures. The International Space Station, which orbits just 400 kilometers above Earth and receives regular resupply missions, has backup systems for its backup systems, and they still face critical failures that require immediate attention. On Mars, you don't have the luxury of regular resupply. You don't have backup systems arriving every few months. You have what you brought, and when it breaks, you either fix it with whatever materials you have on hand, or people start dying. Let's talk about the air you breathe. On Earth, you don't think about it. You just inhale, and oxygen flows into your lungs at a partial pressure your body has evolved over billions of years to process. On Mars, there is no breathable atmosphere. The air is 95% carbon dioxide, with a surface pressure less than 1% of Earth's. Every breath a colonist takes on Mars comes from a machine. The ECLSS has to scrub carbon dioxide from the habitat air, split it into carbon and oxygen through chemical or electrolytic processes, manage humidity levels, remove contaminants, and maintain exactly the right pressure and composition. This happens 24 hours a day, 7 days a week, with zero margin for error. Carbon dioxide scrubbers, the kind used on the ISS, need regular replacement. They're not like air filters you change once a year. They saturate quickly and become useless. The Apollo 13 mission nearly ended in tragedy when the crew's CO2 scrubbers couldn't keep up, and they had to jerry-rig a solution using duct tape and spare parts. They were 3 days from Earth. Mars colonists would be months away from any help. Recent research into bioregenerative life support systems using plants and algae to recycle air shows promise but also reveals terrifying fragility. A 2025 study in Nature's NPJ Microgravity Journal highlighted that these biological systems require massive infrastructure, precise environmental control, and constant monitoring. When they fail, and they do fail, they fail catastrophically. Plants die, algae cultures crash, and suddenly your oxygen production drops by whatever percentage that system was providing. You might think, well, we'll have redundancy, multiple systems, and you'd be right to think that, except redundancy means mass. Every backup system is more mass to launch from Earth at approximately $10,000 per kilogram using current technology. Every kilogram of backup equipment is one less kilogram of food, water, tools, or anything else the colony needs. The math becomes brutal very quickly. NASA's current estimates suggest that a sustainable Mars colony of even just 10 people would require hundreds of tons of equipment, supplies, and infrastructure. Getting that to Mars, even with next-generation rockets, would cost tens of billions of dollars, and that's before the first colonist even lands. But let's say we solve the engineering challenges. Let's say we build perfect redundancy into every system. We have stockpiles of every spare part imaginable, and our maintenance crews are trained to fix anything that breaks. We still face a problem that no amount of engineering can solve. Human biology wasn't designed for Mars, and the adaptations required aren't something you can just train for or build around. The human body is a finely tuned machine that evolved over 3.8 billion years to function in one very specific environment, Earth. Every system in your body, cardiovascular, respiratory, skeletal, immune, neurological, calibrated itself through countless generations to operate under Earth's gravity, Earth's atmospheric pressure, Earth's magnetic field, and Earth's 24-hour day-night cycle. Mars breaks every single one of those conditions. Let's start with gravity, because this is where the biological nightmare begins. Mars has 38% of Earth's gravity. That might sound like a fun environment where you can jump higher and lift heavier objects, and for the first few days, it might even feel exhilarating. But your body doesn't care about how fun it feels. Your body cares about maintaining homeostasis, and reduced gravity throws everything off balance. We have extensive data on what happens to humans in microgravity from decades of space station research. Astronauts on the ISS lose between 1 to 2% of their bone density per month. Their muscles atrophy despite rigorous daily exercise routines. Their cardiovascular systems decondition because the heart doesn't have to work as hard to pump blood without gravity pulling it down. Mars isn't microgravity, it's partial gravity. And here's the terrifying part. We have almost no data on what partial gravity does to human physiology long term. Every human who's experienced reduced gravity has either been in freefall orbit or walking on the moon for a few days at most. Nobody has lived for months or years in Martian gravity conditions. The best models we have suggest that Mars gravity might slow the bone loss and muscle atrophy compared to microgravity, but it won't stop it. Your skeleton is constantly breaking down and rebuilding itself. That's normal. On Earth, the stress of gravity signals your bones to rebuild stronger. On Mars, that signal is 62% weaker. Over time, bones become brittle, fractures become common, and healing from those fractures takes longer because the reduced gravity doesn't provide the mechanical stress bones need to rebuild properly. Imagine you're 6 months into your Mars colony mission. A habitat technician slips while repairing an external panel and breaks their femur. On Earth, that's a serious injury requiring surgery, pins, and months of rehabilitation. On Mars, it's potentially catastrophic. You probably don't have the medical equipment for complex orthopedic surgery. The reduced gravity means bone healing will be compromised. The patient needs to stay off that leg, but there's no one to replace them in the maintenance rotation because your colony is running on minimal crew. One injury cascades into missed maintenance cycles, which leads to equipment degradation, which increases the risk of system failures, which puts stress on the remaining crew, which increases the likelihood of more accidents. This is how colonies collapse, not from one dramatic failure, but from cascading problems that overwhelm your ability to respond. The cardiovascular changes are equally concerning. In microgravity, astronauts' hearts become more spherical and lose muscle mass. Blood volume decreases. The autonomic nervous system that regulates blood pressure gets confused. When astronauts return to Earth after 6 months on the ISS, they can barely stand up without nearly fainting because their cardiovascular systems have deconditioned so severely. On Mars, you'd face similar deconditioning, just potentially slower. But here's the critical difference. ISS astronauts know they're coming back to Earth. They know their cardiovascular system only needs to survive the transition back to full gravity. Mars colonists don't have that luxury. They're staying in reduced gravity indefinitely, and we simply don't know what that does to human hearts over years or decades. A 2025 study on physiological challenges of sustained human presence in space found that microgravity-induced health risks remain one of the most significant barriers to Mars colonization. The paper highlighted cardiovascular remodeling, bone density loss, muscle atrophy, and immune system dysfunction as critical concerns that current countermeasures, exercise, medication, diet, can mitigate but not eliminate. And then there's radiation. Oh, the radiation. Earth is protected by 2 incredible shields, a thick atmosphere and a powerful magnetic field. The magnetosphere deflects most of the charged particles streaming from the sun. The atmosphere absorbs much of what gets through. At sea level on Earth, you're exposed to about 0.3 millisieverts of radiation per year from cosmic sources. Mars has no magnetic field. It lost its planetary dynamo billions of years ago when its core cooled and solidified. Its atmosphere is less than 1% the density of Earth's. These 2 factors mean that Mars' surface radiation is fundamentally, horrifyingly different from Earth. NASA's Curiosity rover carries a radiation detector called RAD, the Radiation Assessment Detector. Since landing in 2012, it's been measuring the radiation environment continuously. The data shows that someone standing on the Mars surface would receive about 250 millisieverts per year. That's over 800 times Earth's background radiation. But it gets worse. The radiation on Mars comes in two flavors, both deadly. First, there's solar particle radiation, energetic protons and other particles ejected during solar flares and coronal mass ejections. These can spike radiation levels dramatically during solar storms. Second, and more insidious, is galactic cosmic radiation, high-energy particles from exploding stars across the galaxy. Traveling at nearly the speed of light, galactic cosmic rays are particularly nasty because they're so energetic that they're nearly impossible to shield against without absurdly thick barriers. When these particles hit atoms in the Martian regolith, they can create secondary radiation showers, actually making surface radiation worse in some cases than in open space. The biological effects of chronic radiation exposure are well documented. Increased cancer risk is the obvious one. NASA estimates that a 1,000-day Mars mission would give astronauts approximately a 5% increased lifetime cancer risk, but cancer takes years to develop. The immediate effects are more subtle and more dangerous for a functioning colony. Radiation damages DNA. Your cells have repair mechanisms, but they're not perfect. Accumulated DNA damage affects cognitive function first. Studies on mice exposed to simulated cosmic radiation showed memory impairment, anxiety, and decision-making deficits. In astronauts, this could manifest as slower reaction times, difficulty with complex problem-solving, and increased error rates. Imagine your Colonies engineer trying to diagnose a failing life support system while their brain is literally being damaged by radiation exposure. The pressure is immense. Lives depend on them fixing this problem. But the radiation they've absorbed over the past 6 months has degraded their hippocampus, the part of the brain responsible for memory and spatial reasoning. They're making mistakes they wouldn't have made 6 months ago. They're forgetting steps in the repair procedure. And they don't even realize their cognitive function has declined, because that's one of the symptoms: decreased self-awareness of impairment. This is the invisible crisis that would face every Mars colonist every single day. You can't see radiation, you can't feel it, it doesn't hurt when it hits you, but it's constantly there, degrading your DNA, increasing your cancer risk, and slowly damaging your brain. The standard solution proposed is shielding. Build habitats underground or pile meters of regolith on top of structures to absorb radiation. And yes, that would help. But it creates massive logistical and engineering challenges. To reduce radiation to Earth-like levels, you'd need approximately 3 meters of Martian regolith above you. That's almost 10 feet of compacted dirt and rock. For a small habitat module 10 meters in diameter, that's roughly 700 cubic meters of regolith, weighing about 900 tons at Martian gravity. You'd have to excavate that material, transport it, and pile it on top of a structure strong enough to support the weight without collapsing. On Earth, that's a challenging construction project. On Mars, it's almost incomprehensible. You're working in a pressure suit that limits your mobility. Your construction equipment is solar-powered or runs on batteries that need constant recharging. The dust clogs every mechanism. And you're doing all this while being bombarded by the very radiation you're trying to shield against. The alternative is building underground, which sounds simpler but brings its own nightmares. You need to excavate stable caverns in Martian rock using equipment that probably doesn't exist yet. You need to ensure structural stability without the benefit of detailed geological surveys. You need to create airtight seals in rock that's been fractured by billions of years of temperature cycling and meteorite impacts. And here's what nobody talks about in those sleek Mars colony animations: the psychological toll of living underground on an alien world where you can't step outside without a pressure suit. Humans aren't meant to live in confined spaces with recycled air and artificial light. We evolved as savanna apes who could see the horizon in every direction. Even on Earth, living underground or in windowless environments causes measurable psychological stress. Seasonal affective disorder happens just from reduced sunlight exposure during winter months. On Mars, you'd be living in a sealed habitat with maybe a dozen other people, breathing recycled air, eating hydroponically grown food that lacks the variety and flavor of Earth cuisine, sleeping on a hard bunk, working long shifts maintaining critical systems, and never, ever being able to step outside and feel wind on your face or rain on your skin. The psychological studies on isolated environments, Antarctic research stations, submarines, simulated Mars habitats, consistently show the same patterns. After the initial excitement wears off, usually around the 3 to 4 month mark, mood starts declining, interpersonal conflicts increase, motivation drops, depression and anxiety become common. NASA's CHAPIA simulations, which locked volunteers in a Mars habitat replica for a year, provided crucial data on these psychological challenges. Participants reported feelings of isolation, frustration with repetitive tasks, and interpersonal tension that required constant management and intervention. Now multiply that stress by the knowledge that you can't leave. Earth is months away, accessible only through launch windows that occur every 26 months. If you hate it, if you can't handle the confinement, if you're having a psychological breakdown, too bad. You're stuck there until the next return window. The psychological fragility of isolated groups isn't theoretical, it's documented across centuries of human exploration. Antarctic expeditions in the early 20th century regularly ended with crew members at each other's throats. Modern research stations still experience what psychologists call winter over syndrome, a constellation of symptoms including hostility, depression, sleep disturbances, and cognitive impairment that emerges during the long polar night. And Antarctica is paradise compared to Mars. At least at an Antarctic station, you can radio home with minimal delay. You can evacuate someone having a medical or psychological emergency within hours or days if absolutely necessary. The air outside will kill you from cold, but it won't boil your blood from pressure loss or suffocate you from lack of oxygen. Mars communication has a minimum light speed delay of 3 minutes one way when the planets are closest, extending to 22 minutes when they're on opposite sides of the Sun. That means any conversation with Earth involves waiting 6 to 44 minutes between question and answer. You can't have a real-time conversation with a family member. You can't consult with a specialist about an emergency and get immediate feedback. You send a message and wait. Imagine you're having a panic attack. Your chest is tight. You can't breathe properly. You're convinced something is catastrophically wrong with your body. On Earth, you call emergency services and help arrives within minutes. On Mars, you send a message to the mission psychologist on Earth describing your symptoms. Then you wait 20 minutes for the signal to reach Earth. Then you wait while they formulate a response. Then you wait another 20 minutes for their reply to reach you. By the time you get advice, 45 minutes have passed and you've been spiraling alone in a tin can millions of kilometers from home. The social dynamics of small isolated groups become crucial and potentially lethal. Research on long-duration spaceflight and isolated environments shows that crew cohesion is the single most important factor in mission success. One person with incompatible personality traits or poor coping mechanisms can poison the entire group dynamic. On Earth, if you have a toxic coworker, you go home at the end of the day. You have weekends. You have personal space and privacy. On a Mars colony, that toxic person is there when you wake up, at breakfast, during your work shift, at dinner, and in the sleeping quarters 6 meters away from your bunk. There's no escape. There's no HR department to file a complaint with. There's no option to quit and find another job. And unlike the ISS, where crew rotations happen every 6 months, Mars colonists would be stuck together for years. The energy requirements to send people back and forth mean that early Mars missions would be one-way or at minimum multi-year commitments. You better hope that the selection process for colonists was absolutely perfect, because one person cracking under pressure could take the entire colony down with them. We've seen this play out in simulations. The Mars 500 experiment, conducted by Russia's Institute for Biomedical Problems between 2010 and 2011, locked 6 volunteers in a mock spacecraft for 520 days. Despite extensive psychological screening, crew members reported significant interpersonal conflicts, decreased motivation, and difficulty maintaining mission focus as time dragged on. And that was a simulation. They knew it was fake. They knew they could technically leave if a real emergency occurred. They knew they were in Moscow, not on Mars, and they still struggled. Now layer on real danger, real consequences. The knowledge that a mistake could kill not just you, but everyone depending on the systems you maintain, the constant background radiation accumulating in your tissues, the bone density you're losing every day, the muscle mass wasting away despite exercise protocols, the food that tastes vaguely wrong because it's all grown in hydroponics with artificial nutrients. This is where the cascading failures really begin to accelerate. A psychologically stressed crew makes more mistakes. Mistakes lead to system failures. System failures increase workload and stress. Increased stress degrades performance further. It's a positive feedback loop, spiraling toward catastrophe. Let's talk about food, because this is where the biological and engineering challenges collide in particularly nasty ways. You cannot bring enough food from Earth to sustain a permanent Mars colony. The mass requirements make it impossible. A single person needs approximately 0.6 kilograms of food per day. That's roughly 220 kilograms per year. For 10 colonists over a 2-year period before resupply, you're looking at 4,400 kilograms just for food, not counting packaging and storage systems, so you have to grow food on Mars. There's no alternative, and growing food in controlled environments with artificial light is difficult even on Earth, where you have abundant resources, technical support, and the ability to order replacement parts overnight. The challenge starts with the growth medium. Martian regolith is not soil. Real soil is a complex ecosystem of minerals, organic matter, bacteria, fungi, and countless microorganisms that break down nutrients and make them available to plants. Martian regolith is sterile rock dust laden with perchlorates, toxic chemicals that would kill most Earth plants. NASA researchers have been experimenting with detoxifying Martian regolith simulants. The process involves either washing the soil with massive amounts of water to dissolve and remove the perchlorates, or using specialized bacteria that can metabolize these compounds. Both approaches work in laboratory conditions, but require resources that would be desperately scarce on Mars. Water is the critical limiting factor for everything on Mars. You need it for drinking, about 3 liters per person per day. You need it for hygiene, though this would be strictly rationed. You need it for cooling systems because all your electronic equipment generates heat. And you need enormous amounts for agriculture. A single tomato plant can transpire up to 1 liter of water per day during peak growth. Lettuce, potatoes, wheat, every crop requires water, and in a closed environment you have to recycle every drop. The water recycling systems on the ISS recover about 93% of all water, including from urine and humidity condensation. That's impressive engineering. but 7% loss per cycle adds up quickly when your water supply is finite and resupply is 2 years away. And water isn't just H2O on Mars, it's a resource you have to extract from ice deposits or potentially from hydrated minerals in the regolith. The Phoenix lander confirmed water ice just below the surface in Mars' polar regions back in 2008. More recently, radar mapping has identified vast subsurface ice deposits in mid-latitude regions. But confirming ice exists and actually extracting it are vastly different challenges. You need to excavate through rock-hard permafrost in sub-zero temperatures. You need to melt the ice without losing it to sublimation in the low pressure. You need to purify it because Martian ice likely contains dissolved perchlorates and other contaminants. And you need to do all this using energy-intensive processes on a planet where every joule of electricity is precious. Solar panels on Mars generate about 43% of what they'd produce on Earth due to the increased distance from the sun and atmospheric dust. Dust storms can block sunlight for weeks or months. The global storm that killed Opportunity in 2018 darkened the sky so thoroughly that the rover's solar panels produced essentially zero power for months. You could use nuclear power, radioisotope thermoelectric generators, like those powering Curiosity and Perseverance, but those produce relatively small amounts of electricity, and scaling up to colony-level power requirements would mean bringing multiple nuclear reactors from Earth, each one adding tremendous mass to your payload and creating radioactive waste disposal problems on top of everything else. Energy scarcity means you're constantly making impossible choices. Do you run the water extractor or the oxygen generator? Do you heat the habitat or grow food? Do you recharge the rover batteries or power the communications array? Every decision is life or death, and there's never enough energy to do everything you need simultaneously. Back to agriculture, even if you solve the soil detoxification and water issues, you're still trying to grow plants in artificial light under a rigid schedule. Plants evolved under Earth's sun, which provides a specific spectrum of light at intensities that vary throughout the day and across seasons. LED grow lights can approximate this, but they require enormous amounts of electricity. The energy requirements for feeding 10 people through hydroponics or aeroponics are staggering. Studies on closed-loop life support systems estimate you need approximately 100 square meters of growing space per person to provide adequate nutrition. That's 1,000 square meters for 10 people, roughly the size of 2 basketball courts, all requiring artificial lighting, climate control, nutrient delivery, and monitoring. And here's the problem that agricultural engineers lose sleep over: crop failure. On Earth, if a field fails, you have other fields, other farms, global supply chains. On Mars, if your hydroponic system crashes, people starve. There's no backup grocery store. There's no emergency food delivery. You have whatever dried rations you brought from Earth, and when those run out, you're entirely dependent on what you can grow. Crop failures happen more often than people realize, even in controlled environments. A fungal infection spreads through your lettuce crop overnight. An equipment malfunction causes temperature fluctuations that stress your wheat. A nutrient imbalance in your hydroponic solution leads to stunted growth. Each of these problems is solvable on Earth, where you have laboratories, specialists, and time to diagnose and respond. On Mars, you have limited diagnostic equipment, crew members with basic training trying to consult manuals, and the clock ticking down to when your stored food runs out. The biological research on space agriculture shows just how delicate this balance is. A comprehensive 2025 systems-level review published in Agricultural Journal documented the immense challenges plants grown in reduced gravity show altered root development and nutrient uptake. The closed environment means that any pathogens introduced whether bacterial, fungal, or viral, can spread rapidly through crops with no natural predators or environmental controls to limit them. You might think you'd start with a sterile environment, but that's impossible. Humans carry trillions of microorganisms in and on their bodies. Every time someone enters the growing area, they're potentially introducing bacteria and fungi. Some of these microbes are beneficial or harmless. Others could devastate crops, and in a closed system with no biodiversity, the balance between beneficial and harmful organisms is incredibly fragile. There's also the psychological component of failed crops that nobody talks about. Imagine you're a colonist who's been carefully tending tomato plants for 3 months. You've watched them grow from seeds, carefully monitored their nutrient levels, adjusted the lighting schedule, hand-pollinated the flowers. These plants represent not just food but hope, a connection to earth, to growing things, to life in a dead world. Then you come in one morning and find them wilted, blackened, destroyed by a pathogen or equipment failure you couldn't prevent. That's not just a logistical setback, that's a psychological blow that compounds all the other stresses you're under. And you have to immediately start over, knowing that the next crop might fail too, while your stored food reserves tick steadily downward. The nutrient content of space-grown food is another concern that recent research has highlighted. Plants grown under artificial conditions often have different nutritional profiles than their Earth-grown equivalents. They might produce less of certain vitamins or antioxidants. Over years of eating only artificially grown food with suboptimal nutrition, colonists would face deficiencies that could compromise their already stressed immune systems. Speaking of immune systems, this is where things get genuinely terrifying from a medical perspective. The human immune system is exquisitely sensitive to stress, and Mars colonists would be experiencing multiple simultaneous stresses that we know compromise immune function. Radiation exposure damages bone marrow, where immune cells are produced. Psychological stress elevates cortisol, which suppresses immune response. Poor sleep quality, common in isolated environments and disrupted by Mars's 24-hour and 39-minute day, impairs immune function. Reduced gravity alters how immune cells move and function. Inadequate nutrition from limited diet variety provides insufficient micronutrients for optimal immune performance. Research on astronauts aboard the ISS has documented concerning immune system changes. Studies show reactivation of dormant viruses like Epstein-Barr and varicella zoster, the viruses that cause mononucleosis and shingles. These viruses lie dormant in most adults, but reactivate when immune surveillance drops. On Earth, this might mean you get a cold sore or feel run down. On Mars, it could mean a severe illness with no adequate medical facilities to treat it. And here's the nightmare scenario that medical planners wargame constantly: a serious illness or injury that requires surgery. Let's say a colonist develops appendicitis. On Earth, that's a routine emergency surgery, appendectomy, overnight hospital stay, recovery at home. On Mars, you probably don't have a trained surgeon. You might have a physician's assistant or paramedic with emergency medical training, but performing an appendectomy requires skill, experience, and equipment. Do you have a proper sterile surgical suite? Do you have anesthesia and the ability to monitor vitals during surgery? Do you have blood for transfusion if something goes wrong? Do you have antibiotics for post-surgical infection? And if so, how much of your limited pharmaceutical supply are you willing to use on one person? These aren't hypothetical questions. A 2024 study on medical risks and potential surgical conditions during Mars missions identified dozens of surgical emergencies that could occur: appendicitis, bowel obstruction, traumatic injuries requiring amputation, dental emergencies requiring extractions, even emergency cesarean sections if your colony includes reproductive age women. Which brings up another biological complication nobody wants to discuss: reproduction. If you're establishing a permanent colony, eventually the question of children arises, and we have absolutely no data on human reproduction, fetal development, or child growth in reduced gravity. Animal studies provide disturbing hints. Pregnant rats in simulated microgravity showed abnormal fetal development. Studies on fish and amphibians in space revealed developmental problems and reduced survival rates. The mechanical stresses of development, how cells migrate, how organs form, how bones grow, all depend on gravity cues that simply don't exist properly on Mars. Even if a fetus developed normally, what about childbirth? Labor and delivery are already risky, even with modern medical facilities. On Mars, you'd be dealing with reduced gravity, affecting fluid dynamics and contractions, limited medical equipment, no emergency neonatal intensive care, and a mother whose bone density and cardiovascular fitness have been compromised by months or years in Martian gravity. And if the child is born healthy, they'd grow up in reduced gravity with unknown long-term consequences. Would their bones develop properly? Would their heart grow strong enough? Would their vestibular system, which governs balance and spatial orientation, develop correctly in 38% gravity? We simply don't know. And the ethical implications of experimenting on human children in an environment that might permanently disable them are staggering. Let's shift to another failure mode that's less dramatic but equally catastrophic: supply chain breakdown. Every colony depends on regular resupply missions from Earth, bringing spare parts, pharmaceuticals, specialized equipment, and items that simply can't be manufactured on Mars with limited industrial capacity. These resupply missions are subject to the same orbital mechanics that govern all interplanetary travel. Launch windows occur every 26 months when Earth and Mars align favorably. If you miss a window due to rocket failure, budget cuts, political changes on Earth, or any of 1,000 other reasons, your next opportunity is more than 2 years away. Now imagine you're a Mars colonist and you receive word that the scheduled resupply mission has been delayed. Maybe the launch failed, maybe funding was cut, maybe Earth is dealing with a crisis and Mars just isn't a priority anymore. You're now looking at stretching your resources for an additional 26 months beyond what you planned for. Pharmaceuticals are a particular concern. Medications have expiration dates, and many drugs degrade faster under radiation exposure. Your colony's medical supplies were calculated for a specific time frame. Now you need to ration everything: pain medications, antibiotics, anti-inflammatory drugs, psychiatric medications that some crew members might depend on for pre-existing conditions. Spare parts for critical systems become precious artifacts. Every time something breaks, you have to decide whether to use one of your limited spares or try to jury-rig a repair with whatever materials you have available. And every jury-rigged repair is a potential point of failure, a weakness in systems that cannot afford weakness. The psychological impact of a delayed or cancelled resupply mission would be devastating. Colonists would feel abandoned, forgotten by Earth. The tenuous thread connecting them to home would feel even more fragile, and the knowledge that their survival depends entirely on decisions made by people 300 million kilometers away, people who might have very different priorities, would be crushing. There's also the very real possibility that Earth simply loses interest. History is littered with exploration outposts that were abandoned when political will shifted or economic priorities changed. The Norse settlements in Greenland collapsed in the 15th century, partly because supply ships from Europe stopped coming. Antarctic bases have been evacuated and abandoned when funding dried up. Mars colonies would face the same risk, except the consequences of abandonment would be measured not in hardship but in body counts. Public attention is fickle. The first Mars landing will be the most watched event in human history. The second landing will get significant coverage. By the 5th or 10th mission, it'll be background noise. And when budgets get tight, when Earth faces its own crises, economic collapse, climate disasters, political upheaval, the billions required to keep Mars colonies supplied will look increasingly difficult to justify. This isn't cynicism, it's pattern recognition. The Apollo program landed humans on the Moon 6 times between 1969 and 1972, then abruptly ended. Not because we'd learned everything there was to learn, but because political priorities shifted and the money went elsewhere. We haven't sent humans beyond low Earth orbit in over 50 years. What makes anyone think Mars will be different? Now let's discuss something that sounds mundane but would grind a Mars colony to a halt faster than almost anything: waste management. Every human produces waste: biological waste, packaging waste, broken equipment, worn-out clothing, everything. On Earth, you throw things away and they disappear into a vast waste management infrastructure. On Mars, nothing disappears, everything accumulates. Biological waste is particularly challenging. Each person produces roughly 150 grams of feces and 1 to 2 liters of urine daily. That waste contains water, nutrients, and potentially harmful pathogens. You can't just dump it outside. The perchlorates and radiation would prevent any natural decomposition, and you'd be creating a toxic waste pile that could contaminate water ice you might need to extract later. The solution is complex recycling systems that process human waste to extract water, recover nutrients for agriculture, and safely dispose of or repurpose the remaining solids. The ISS does this with impressive efficiency, but those systems require constant maintenance, specialized filters that need replacement, and significant energy input. On Mars, your waste processing systems would be handling not just human biological waste but also agricultural waste, dead plants, root systems, plant material you can't eat. All of this organic matter needs to be processed, either composted for soil amendment or broken down to recover nutrients. And any failure in these systems means waste accumulates, water isn't recycled, nutrients aren't recovered, and your closed-loop life support begins to break down. Then there's equipment waste, broken tools, burned-out electronics, worn-out clothing, damaged pressure suits. All of this accumulates. Some materials can be recycled if you have the right equipment and energy budget. Metals can be melted down and reformed, though this requires significant energy. Plastics are harder. You need specific recycling equipment for different polymer types. And some materials, like composite structures or specialized electronics, simply can't be recycled with the limited industrial capacity a small colony would have. The mass balance becomes a slow-motion disaster. You're bringing finite resources from Earth, using them, and generating waste that can't be fully recycled, even with 95% recycling efficiency, which would be extraordinarily good. 5% loss per cycle means your resources steadily decline. Over months and years, that accumulates into critical shortages. Water loss is the most concerning. Despite your best recycling efforts, water escapes. Some is lost during airlock cycling. The air you vent contains water vapor. Some is locked up in waste that can't be fully processed. Some is lost to leaks in pipes and seals that you can't completely eliminate. The ISS loses water constantly and requires regular resupply to make up the deficit. On Mars, every kilogram of water you lose is one you have to extract from ice deposits through energy-intensive processes. Atmosphere loss is another slow bleed that compounds over time. Your habitat is pressurized to roughly 80 kilopascals, about 80% of Earth's sea level pressure. Outside is 0.6 kilopascals, essentially vacuum. Every time an airlock cycles, you lose atmosphere. Every tiny leak in seals and joints costs you precious breathing gas. You're constantly needing to manufacture replacement atmosphere by extracting oxygen from CO2 or splitting water, both energy-intensive processes. The mathematics of closed-loop life support are unforgiving. You need near-perfect recycling efficiency to sustain a colony long-term, but perfect systems don't exist. Engineering tolerances, mechanical failures, and thermodynamic limits guarantee losses. And on Mars, losses can't be easily replaced. Let's talk about a failure mode that's almost never discussed in Mars colonization plans: dust infiltration into habitats. Martian dust isn't just an external problem for rovers and solar panels, it's an existential threat to human health inside supposedly sealed habitats. The dust particles are incredibly fine, averaging around 3 micrometers in diameter. That's small enough to penetrate door seals, gasket joints, and filter membranes designed for much larger particles. And because the dust is electrostatically charged, it actively clings to surfaces and works its way into every crevice. Every time colonists go outside and return through an airlock, they bring dust with them. It's on their suits, embedded in fabric, clinging to equipment. You can brush off the visible dust, but the microscopic particles remain. Over time, despite your best efforts, dust accumulates inside the habitat. Remember those perchlorates in the soil. They're now in the air you're breathing. Recent 2025 research on Martian dust health impacts confirmed that perchlorate exposure through inhalation and dermal contact would present serious hazards. The particles themselves are physically irritating to lung tissue, sharp, abrasive, and small enough to reach deep into alveoli where gas exchange occurs. Chronic dust exposure would lead to a Martian version of pneumoconiosis, lung disease caused by inhaling mineral dust. On Earth, coal miners and construction workers develop this after years of exposure. On Mars, colonists would be breathing contaminated dust daily in a confined space with no escape. Over months, respiratory function would decline, coughing would become chronic, lung capacity would drop, and your already compromised immune system would struggle to clear the particles and fight off respiratory infections. The dust also wreaks havoc on equipment inside habitats. It gets into computer cooling fans, causing them to overheat. It abrads mechanical components, accelerating wear. It contaminates food preparation areas. It covers optical sensors, giving false readings. There's no way to eliminate it completely, only manage it, and that management requires constant vigilance and resources you can barely spare. Air filtration systems would need replacement filters constantly. HEPA filters rated for 0.3 micrometers can catch most Martian dust, but they clog quickly when dealing with high particulate loads. And each filter replacement uses resources you brought from Earth or manufactured from limited local materials. The insidious nature of dust infiltration is that it's gradual. Day 1, your habitat is pristine. Day 30, there's barely noticeable dust. Day 90, surfaces need daily cleaning. Day 180, crew members are developing respiratory symptoms. Day 365, lung function tests show concerning declines and equipment is failing from accumulated dust damage. By the time you realize the severity of the problem, your colony's health and infrastructure are already compromised. Now let's examine what happens when multiple systems start failing simultaneously. Because on Mars, Murphy's Law doesn't just apply, it multiplies. Engineers call this cascading failure, and it's the nightmare scenario that turns manageable problems into colony-ending catastrophes. Picture this timeline. Month 3 of your Mars colony operation. A dust storm reduces solar panel efficiency by 40%. Your energy budget is now critically constrained. You make the decision to reduce heating in non-essential areas to conserve power for life support and food production. The temperature drop in the storage module, just a few degrees, causes a seal to contract slightly. It's within engineering tolerances, barely worth noticing. but that tiny gap allows humidity to condense and freeze in the seal gap. Over the next week, repeated freeze-thaw cycles as the module temperature fluctuates begin to degrade the seal material. Meanwhile, your crew is working overtime to clean solar panels and restore power generation. They're exhausted, sleeping less, stress hormones elevated. One of your hydroponics technicians, working on 4 hours of sleep, miscalculates a nutrient formula. The plants don't die, that would be obvious, but their growth rate slows by 15%. You won't notice for another 2 weeks when harvest yields come up short. The degraded seal in the storage module finally fails in week 5. Pressure drops trigger an alarm. Your maintenance crew responds, but to fix the seal properly, they need to depressurize the module, go EVA, extravehicular activity, and replace the damaged component. That's a 6-hour operation requiring 2 crew members in pressure suits. While they're working on the seal, the life support system in the main habitat develops a problem. The CO2 scrubber is showing elevated carbon dioxide levels, not dangerous yet, but trending wrong. Your remaining crew has to diagnose this while short-handed because 2 people are outside. They trace it to a clogged filter that should have been replaced last week, except the persons responsible for that maintenance was helping clean solar panels. They replace the filter, but in their hurried work they don't quite seat it correctly. It's functional but suboptimal. CO2 levels stabilize, but at slightly higher than ideal concentrations. Nobody notices the mild headaches that start affecting crew members because everyone's stressed and sleep-deprived anyway. Meanwhile, your food production is now running behind schedule because of that earlier nutrient miscalculation. You're going to come up short on this month's harvest, which means dipping into stored rations. That's fine. You have reserves for exactly this kind of shortfall, except those reserves are stored in the module that just experienced pressure loss. You open the containers and find that freeze-drying from the pressure drop has degraded some of the food. Still edible, but you've lost perhaps 10% of that reserve stockpile. This is month 3. You have these problems mostly under control, but you're already depleting reserves, running crew ragged, and experiencing system degradations that will compound over time. And you're doing this on a planet that offers no mercy, no second chances, and no rescue options if things truly go sideways. The chronic elevated CO2 levels, barely above normal, nothing that would trigger emergency protocols, are subtly affecting cognitive function. Crew members are making slightly more errors in judgment. A recent study on cognitive performance in elevated CO2 environments showed measurable declines in decision-making ability at concentrations as low as 1,000 parts per million, well below dangerous levels, but enough to impair complex problem-solving. By month 4, you're seeing the second-order effects. The crew member who miscalculated the nutrients is now making more frequent mistakes. The seal repair that was rushed needs to be redone because it's leaking again. Equipment that should have been maintained wasn't because everyone was firefighting immediate problems. And then the solar panels that you worked so hard to clean start showing reduced efficiency anyway. Because it's not just dust accumulation, the panels themselves are degrading from radiation exposure and extreme temperature cycling. Every Martian night, temperatures plunge to minus 100 Celsius. Every day, they climb to perhaps minus 20. The panels experience this thermal stress cycle every 24.6 hours, expanding and contracting, developing microfractures in the semiconductor materials. On Earth, solar panels are rated for 25 years of operation, but that's under Earth conditions: protective atmosphere, moderate temperature ranges, no perchlorate dust, minimal radiation. On Mars, those same panels might last 5 years if you're lucky, and you don't have the industrial infrastructure to manufacture replacements. When they fail, your power budget drops permanently. Nuclear power sources like radioisotope thermoelectric generators also degrade over time as the radioactive material decays. Curiosity and Perseverance both use plutonium that lose about 3% of their power output per year. That's acceptable for a rover designed for a limited mission duration, but for a permanent colony, it means your baseline power budget is constantly declining. This energy scarcity forces impossible choices. Do you maintain full life support and let food production suffer? Do you reduce habitat heating to dangerous levels to keep the greenhouses warm? Do you shut down non-essential systems? But what qualifies as non-essential when every system contributes to survival? Water recycling is particularly energy-intensive. The processes to purify water from waste, filtration, distillation, chemical treatment, UV sterilization, all require significant power. If you cut energy to water processing to save power elsewhere, your water quality degrades. Higher contaminant levels stress your already compromised immune systems. Gastrointestinal issues start appearing. Crew health deteriorates further. If you are still watching, make sure to subscribe to the channel. Your support means a lot to me. The medical challenges would accelerate as months progress. Remember that radiation exposure we discussed. By month 6, crew members have accumulated approximately 125 millisieverts, equivalent to several hundred chest X-rays. Cancer risk is climbing, but the immediate concern is immune suppression and increased infection susceptibility. Someone develops a respiratory infection, could be bacterial, could be viral, possibly from reactivated dormant viruses due to immune stress. On Earth, this is a week of rest and maybe antibiotics. On Mars, you can't afford to have someone out of the work rotation for a week. The colony runs on minimal crew with no redundancy. Everyone is essential, so the sick crew member keeps working, takes whatever medications you have available, and tries to push through. The infection spreads to other crew members because you're living in close quarters with recycled air. Now you have multiple people operating at reduced capacity, depleting your medical supplies faster than planned, and stressing the life support systems that have to handle increased pathogen loads. The habitat's air handling system is designed to filter particulates and scrub CO2, not to handle airborne pathogens like a hospital isolation room. In the enclosed environment, infectious diseases spread with terrifying efficiency. One study of disease transmission in enclosed environments, submarines, spacecraft, Antarctic stations, showed that respiratory infections typically spread to 70 to 100% of inhabitants within days. By month 7, your colony is running on depleted reserves. Degraded equipment, exhausted crew, and accumulated health problems. You haven't had a catastrophic failure, no explosive decompression, no complete life support breakdown. Just steady erosion across every system simultaneously. This is what colonization advocates don't tell you when they show those gleaming habitat renderings. It's not one dramatic disaster that kills a Mars colony. It's the slow, grinding accumulation of small failures, each one manageable in isolation but collectively overwhelming. It's death by 1,000 cuts, played out in slow motion across months while Earth watches helplessly from millions of kilometers away. And we haven't even discussed what happens when a truly critical system fails completely. Let's run through that nightmare scenario. Your primary oxygen generation system stops working. On the ISS, this actually happened in 2021. The Russian Zvezda module's oxygen system failed, and crew had to rely on backup systems while they repaired it. They had multiple redundant oxygen generation methods, including solid fuel oxygen generators that can be activated as emergency backups. And they had Earth just a few hours away if evacuation became necessary. On Mars, your oxygen comes from splitting carbon dioxide using the MOXIE process. Mars Oxygen in Situ Resource Utilization Experiment, which Perseverance has been testing since 2021. It works, producing about 10 grams of oxygen per hour under ideal conditions, but it requires significant electrical power, operates at extremely high temperatures around 800 Celsius, and has components that wear out from thermal stress. When your MOXIE unit fails, you have backup systems. Hopefully, maybe you have chemical oxygen generators, though these consume resources you can't replace. Maybe you have a secondary MOXIE unit, but if the failure was caused by something environmental, like perchlorate dust contaminating components, your backup faces the same failure mode. Your oxygen reserves give you maybe 48 to 72 hours to fix the problem. That sounds like adequate time until you factor in the realities of diagnosis and repair on Mars. First, you have to identify exactly what failed. Is it the electrolysis cell, the heating element, the power supply, the CO2 compression system? Each component requires different diagnostic procedures and specialized tools. You're doing this diagnosis while wearing pressure suits if the habitat pressure is dropping, or while breathing air that's getting progressively higher in CO2 and lower in oxygen if the habitat is sealed. Cognitive function degrades rapidly as oxygen levels drop. At 15% oxygen, down from Earth's 21%, you experience impaired coordination and judgment. At 10%, you lose consciousness, so you're racing against both the clock and your own declining mental capacity to diagnose a complex electromechanical system that's operating at temperatures that can melt metal, using tools that may not have been designed for this specific repair, while consulting technical manuals and possibly trying to get advice from Earth with a 20-minute communication delay. Let's say you identify the problem, a failed heating element in the MOXIE unit. Do you have a replacement? If yes, can you install it properly under time pressure with impaired judgment from rising CO2 levels? If no, can you fabricate a replacement from materials on hand? This is where the fantasy of living off the land on Mars collides with thermodynamic reality. You can't just whip up a replacement heating element rated for 800 Celsius operation from spare parts. These components are engineered from specific materials, often exotic alloys or ceramics, manufactured to precise tolerances using industrial processes that don't exist on Mars. Your best hope is jury-rigging a temporary solution that might work long enough to restore oxygen production while you frantically message Earth requesting a replacement part on the next cargo flight, which won't arrive for 18 to 26 months. Can your temporary fix last that long? Can your crew maintain it under constant stress, knowing their lives depend on a patch job? This is assuming the failure is something mechanical you can potentially fix. What if it's something more fundamental? What if the Martian environment itself is causing failures faster than you can compensate for? Perchlorates aren't just toxic to humans, they're corrosive to many materials, especially at the high temperatures where oxygen generation operates. Over time, perchlorate contamination could degrade seals, corrode electrical contacts, and compromise structural components in ways that aren't immediately obvious but accumulate until catastrophic failure. Temperature extremes create another relentless degradation mechanism. Materials expand and contract with temperature changes. On Mars, you're experiencing temperature swings of 120 Celsius or more between day and night. Metal fatigues, plastic becomes brittle, seals crack. Every component is aging in dog years compared to their Earth-rated lifespans. Radiation causes insidious damage to materials, especially polymers and electronics. The cosmic rays that are damaging colonists' DNA are simultaneously degrading the plastic insulation on electrical wiring, embrittling rubber seals, and causing bit flip errors in computer memory. A 2024 study on radiation effects on materials showed that polymers exposed to Mars-equivalent radiation doses became significantly more fragile within 2 years. Your colony's computers and control systems face constant radiation-induced errors. On Earth, cosmic ray bit flips are rare enough that standard error correction handles them. On Mars, the radiation environment is so harsh that you'd need extensive radiation hardening for all electronics, which adds mass, cost, and complexity. And even hardened electronics eventually accumulate enough damage that failures become common. Imagine your habitat environmental controls are managed by a computer system that's experiencing increasing numbers of radiation-induced errors. A bit flips in the temperature control algorithm, causing the system to slightly overheat one module. The overheat triggers a cascade of sensor readings that the damaged computer misinterprets. It makes a correction that actually makes things worse. By the time humans notice something's wrong, the automated system has spent 6 hours fighting itself and wasting energy. You restart the system, run diagnostics, maybe reload software from backup. It works for a while. Then another cosmic ray hits another critical bit of memory. Then another. The computer systems that govern your life support are slowly being corrupted by an invisible enemy you can't shield against completely. This is the reality of operating complex technical systems in deep space environments. The ISS experiences this. They've had computer failures, radiation-damaged components, and systems that behave unexpectedly. But the ISS can receive replacement computers from Earth within months, and crew rotations mean that equipment issues are someone else's problem after 6 months. Mars colonists can't rotate out. They can't get replacement parts quickly. They're stuck nursing increasingly unreliable systems with dwindling resources and no exit strategy. Let's talk about what happens when the psychological pressure becomes unbearable. You're 7 months into the mission. Systems are degrading. Food is short because crop yields keep disappointing. Someone is chronically ill. Everyone is exhausted. The recycled air smells faintly of chemicals and human bodies, no matter how well the scrubbers work. The food tastes like cardboard. You haven't felt natural wind or rain in 7 months. You haven't seen anyone outside your crew of 10 people. Your family on Earth feels like characters in a story. Their messages arriving with 20-minute delays that make real conversation impossible. And then someone breaks. Maybe it's explosive, a screaming argument over something trivial that escalates because everyone's at their breaking point. Maybe it's quiet. Someone stops getting out of their bunk, stops eating, stops caring. Depression, anxiety, post-traumatic stress, psychotic breaks. All of these have occurred in isolated environments, even on Earth, where help is potentially available. On Mars, you don't have a psychiatrist in person. You might have psychiatric medications, but supplies are limited and doses can't be adjusted easily without real-time consultation. You definitely don't have secure isolation facilities if someone becomes a danger to themselves or others. A crew member experiencing a psychological crisis isn't just a personal tragedy, they're an operational catastrophe. Every person in your colony is essential to operations. Losing one person to psychological breakdown means their workload has to be distributed among remaining crew members who are already stretched beyond sustainable limits. And psychological issues are contagious in confined populations. One person's breakdown increases stress for everyone else. The visible evidence that someone couldn't handle the pressure makes everyone question their own stability. Can I make it? Will I be next to crack? The psychological cohesion that's absolutely essential for survival starts fracturing. Historical cases from extreme environments show how quickly group psychology can deteriorate. The Soviet Salyut 7 space station experienced a mission in 1982 where cosmonauts Berezovoy and Lebedev spent 211 days in orbit and returned barely speaking to each other, their relationship destroyed by the confined isolation. Antarctic winter-over crews have documented cases where team members stopped communicating entirely, leaving notes instead of speaking, despite living in the same small station. These were trained professionals, psychologically screened, who knew they'd eventually return home, and they still experienced breakdowns in social cohesion. Now imagine that same pressure cooker on Mars, where there's no definite return date, where the stakes are literal survival, and where the environment outside will kill you in seconds. The loss of social cohesion doesn't just make people miserable, it makes the colony operationally non-functional. Effective teamwork requires communication, trust, and coordinated effort. When crew members aren't speaking to each other, critical information doesn't get shared. When people don't trust each other, they work in isolation instead of collaborating. When someone makes a mistake, others might not catch it or might not care enough to correct it. And mistakes on Mars are often fatal. A crew member who stopped caring about their own survival might forget to double-check a seal before an airlock cycle. Someone harboring resentment toward another crew member might deprioritize repairing equipment that person depends on. These aren't malicious acts necessarily, they're the subtle degradation of the vigilance and mutual support that keeps everyone alive in an unforgiving environment. There's also the very real possibility of sabotage, either deliberate or subconscious. A psychologically disturbed individual might rationalize that ending the mission and everyone's suffering is actually merciful. Or they might not be thinking rationally at all, just acting on impulses driven by damaged neural chemistry from radiation exposure, chronic stress and isolation. You can't put someone in restraints for months. You can't exile them from the colony. There's nowhere for them to go. You can't even effectively isolate them because the habitat is too small and every person is needed for essential functions. You're stuck in an impossible situation with no good options. Now let's examine the final category of cascading failures, the ones that originate from Earth. Your colony's survival depends on decisions made by people who've never experienced Mars, who are responding to political and economic pressures that have nothing to do with your situation, and who might simply decide that continuing support isn't feasible or worthwhile. Funding for space programs is notoriously volatile. The US Congress has to appropriate NASA's budget every year, and priorities shift with political winds. Private companies are accountable to shareholders who want returns on investment. If a Mars colony isn't producing economic value, and early colonies almost certainly won't, how long will funding continue when there are pressing problems on Earth demanding resources? Climate change, pandemics, economic crises, wars, any major Earthside catastrophe could redirect resources away from Mars support. And unlike Antarctic research stations that can be evacuated within days or weeks, Mars colonies would require continued support for years, even during an orderly shutdown. Assuming you could even bring everyone home, the grim calculus might conclude that it's cheaper to let the colony fail than to maintain support. After all, the people who volunteered for Mars knew the risks, right? They signed waivers. They understood it might be a one-way trip. When budgets get tight and politicians need to make hard choices, how long will public sympathy for distant Mars colonists outweigh immediate problems affecting millions of voters on Earth? This isn't cynical speculation, it's how resource allocation actually works when push comes to shove. The Jamestown colony in Virginia nearly collapsed multiple times between 1607 and 1610 because supply ships from England were delayed or diverted to more profitable ventures. The colonists resorted to cannibalism during the starving time of 1609 to 1610, and that was just across the Atlantic Ocean, a few months' voyage. Mars is orders of magnitude more distant, more expensive to reach, and produces no economic return that would justify continued investment during hard times. Your colony might receive messages from Earth expressing sympathy and explaining that the next cargo mission has been delayed indefinitely due to budget reallocation. You're on your own. Good luck. Even without deliberate abandonment, Earthside supply chains can fail in ways that doom Mars colonies. The rockets that carry cargo to Mars are complex machines with failure rates around 2 to 5%, even for well-established systems. SpaceX's Falcon 9 has been remarkably reliable, but it's still experienced failures. The larger Starship system designed for Mars missions is still in testing and will inevitably experience failures during development and early operational phases. A cargo mission failure means your expected supplies don't arrive. If that cargo included critical spare parts, pharmaceuticals with expiration dates approaching, or food to supplement your limited agricultural production, you're suddenly facing shortages with no backup plan. The next launch window is 26 months away. Multiple consecutive mission failures, statistically inevitable over enough attempts, could leave a Mars colony without resupply for 4 years or more. No colony design I'm aware of accounts for that scenario, because it would require such massive redundancy and stockpiling that the initial mission mass becomes prohibitive. There's also the nightmare scenario of a launch disaster that kills crew or destroys infrastructure on Earth, leading to a grounding of the entire Mars program while investigations proceed and systems are redesigned. The Space Shuttle program was grounded for 32 months after Challenger and 29 months after Columbia. During those periods, the ISS construction was delayed and crews couldn't be rotated. If a Mars cargo system experiences a catastrophic failure, rocket explosion on the pad, collision during orbital assembly, failed orbital insertion, the political and safety review process could ground flights for years. Your colony doesn't have years, you have months of consumables and degrading equipment. Even assuming Earth maintains consistent support, there's the problem of technological obsolescence and infrastructure decay. The systems designed to support the first Mars colony will be based on technology available at launch. But technology advances rapidly. Within 5 years, newer, better systems will exist on Earth that the colony can't access because switching infrastructure is impossible. Your colony is locked into using systems that become increasingly outdated, harder to support, and more difficult to maintain as the institutional knowledge behind them fades. The engineers who designed your life support systems retire or move to other projects. Documentation gets lost or corrupted. The supply chain for replacement parts dries up as manufacturers discontinue old components. This is a problem even on Earth. Try finding replacement parts for electronics from 20 years ago. On Mars, where every component is custom designed for extreme environments and produced in small quantities, obsolescence happens even faster. You're maintaining museum pieces with improvised solutions because the expertise and infrastructure to properly support them no longer exists. Let's talk about what the final collapse actually looks like, because it won't be dramatic. There won't be a single catastrophic moment that makes for good disaster movies. It'll be a whimper, not a bang. Month 9. Your primary water recycling system is operating at 70% efficiency, despite constant repairs. You're supplementing by melting ice, but the energy cost means you've had to reduce food production lighting by 20%. Crop yields are down 30% from projections. You're rationing food, and everyone has lost weight. Morale is rock bottom. 2 crew members are chronically ill with respiratory problems from dust exposure and compromised immune systems. They can't perform physical labor effectively, so the remaining 8 are covering their workload on reduced caloric intake. Someone develops a dental abscess, a cracked tooth from eating the increasingly tough dehydrated rations. The infection requires antibiotics from your dwindling medical supplies, and the pain reduces their work capacity for 2 weeks. Your solar panels are operating at 55% of their original capacity from combined dust accumulation, radiation damage, and thermal stress degradation. The backup nuclear RTG has declined to 82% output from radioactive decay. You're running a chronic energy deficit, which means you're making impossible choices every day about what systems get power. The habitat temperature is kept lower than comfortable to save energy, 15 Celsius instead of 20. Everyone's is cold all the time, which increases caloric requirements you can't meet, suppresses immune function further, and adds to the general misery. Sleep quality deteriorates in the cold, which compounds cognitive impairment from chronic stress and elevated CO2. 3 separate pressure suit failures in the last month mean you're down to 7 functional suits for 10 people. EVA operations are now critically limited. You can't send people outside to clean solar panels or make repairs unless absolutely essential because the suits are literally wearing out and you lack materials to properly fix them. The communications array develops an intermittent fault. Sometimes you can talk to Earth normally, other times messages don't get through or arrive corrupted. You've traced the problem to radiation damage in a component you can't replace. You're losing your lifeline to home, the psychological connection that's been keeping people sane. One of your 2 remaining MOXIE oxygen generators starts producing oxygen contaminated with trace perchlorates that shouldn't be there. The contamination is low enough that it won't kill anyone immediately, but breathing it chronically is adding to the toxic load everyone's accumulating. You can't figure out where the perchlorates are coming from. Somewhere in the system, dust infiltration has contaminated components in a way you can't isolate and fix. Month 10, a crew member attempts suicide. Maybe they succeed, maybe they're stopped in time. Either way, the colony is now in full psychological crisis. The suicide attempt forces everyone to confront what they've been trying to deny. This isn't working. They're not going to make it. The dream of Mars colonization is dying around them, and they might die with it. Emergency psychological consultations with Earth become hourly, except the communication delay makes them almost worthless. The advice from Earth's psychiatrists, reduce stress, ensure adequate rest, maintain social bonds, is laughably impractical when stress is unavoidable. Rest is impossible because systems need constant maintenance, and social bonds are fracturing under pressure. Command structure breaks down. The mission commander has lost authority because their orders are increasingly impossible to follow. Maintain morale when everyone is cold, hungry, sick, and terrified. Complete scheduled maintenance when there aren't enough functional tools or healthy crew members. Stay optimistic when every system is degrading and resupply is months away at best. Some crew members advocate for emergency evacuation, fire up the return vehicle and go back to Earth immediately. Mission failure be damned, at least they'd survive. Others argue that's giving up, that they can still salvage this if everyone just tries harder, works longer hours, makes do with less. The arguments become vicious because they're arguments about survival versus pride, fear versus hope, except the return vehicle might not even be functional anymore. It's been sitting on the Martian surface for 10 months exposed to temperature extremes, radiation, and perchlorate dust. The fuel has been cryogenically stored, which requires power you've been struggling to provide. The systems haven't been test-fired because you can't afford to waste fuel, and the launch window physics mean you need to leave within a specific time frame, or wait another 2 years, and you definitely won't survive another 2 years. Month 11, decision time. Do you attempt emergency departure in a vehicle that might fail, knowing that launch failure means instant death for everyone aboard? Or do you stay and try to survive until the next scheduled resupply mission arrives in 7 months, knowing that your degrading systems probably can't sustain life that long? Some crew members want to stay, some want to leave. The group fractures into factions, arguments become physical altercations because everyone is beyond rational thought, malnourished, oxygen deprived, radiation damaged, psychologically shattered. This is how the Mars colony ends, not with a dramatic explosion or a dust storm that buries the habitat, with exhausted, sick, traumatized people making impossible choices in a deteriorating environment that offers no good options. If they attempt launch and succeed, they return to Earth as failures, the colonists who gave up, who couldn't hack it, whose weakness doomed humanity's Mars ambitions. They'll face years of debriefing, medical treatment for radiation damage and bone loss, psychological counseling for trauma, and public scrutiny over what went wrong. If they attempt launch and fail, they die instantly in a spectacular fireball that will be analyzed for decades to determine what went wrong. Their deaths used to justify either continuing Mars efforts with lessons learned or abandoning the dream entirely. If they stay, they face a slow decline as systems fail one by one. Maybe the next resupply mission arrives in time and saves them. More likely, some combination of life support failure, medical emergency, equipment breakdown, or psychological collapse kills them first. Their last messages to Earth will be increasingly desperate, then resigned, then perhaps silent as power fails and communications go dark. Future missions, if there are future missions, will find the habitat preserved in Mars's thin atmosphere like a tomb, equipment frozen in place, personal effects left where they fell, maybe bodies freeze-dried by the Martian environment. Archaeologists from Earth, studying the first Mars colony's failure the way we study Scott's doomed Antarctic expedition or the Franklin expedition's disappearance in the Arctic. The bitter irony is that each colonist probably volunteered believing they were part of humanity's greatest adventure. They passed rigorous selection. They trained for years. They believed in the mission, in the importance of making humanity multiplanetary, in the romance of exploration and pioneering. And they ended up as a cautionary tale about hubris, about attempting to colonize an environment so fundamentally hostile that no amount of technology or determination could overcome the basic thermodynamic and biological realities.